voice will be listened by only speaker. I think so. Because it is. So this has mic also. So when he speaks, I think mic and receiver. They use earphone, right? I don't know if it work like that or. Hello, 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 hello. Hello. Let's say someone in query is online mode. Query will be listened by only speaker.
Speak via audio, you should be able to hear it. And we have to see whether this is connected. Another 5 minutes. Yeah. Yeah. Please. Yeah, please. Better please join the Zoom session. So that, we are also trying to connect it via. One is HTML. This is HTML?
Yeah.
HTML too. Is there something else you need to do? Or? No. Maybe you can join the Zoom meeting and you just present to the Zoom. Like now the Zoom screen, so people can see here, and it will also go via. Yeah. But I don't know why it's not working.
But here actually we need to change to HDMI.
Yeah, HDMI too. I think it was
Oh, I think. Yeah.
Yes.
Oh, what a full white one.
I think it was not using
It was not. Yeah. I mean, we need to change.
Actually, pressed,
Okay. So now it's good.
but you still need to log in for your
Zoom.
Zoom. Where it will.
Yeah. Need to share the slide, please. In that case, also like, we need to in this.
Where can I find the Zoom links? Zoom links. I didn't receive any Zoom link, I guess.
I shared you the link.
No, I think.
So I'm using my.
So please connect to the Zoom.
Oh,
yeah.
Zoom back. Zoom, but he will log in to Zoom.
I need to log in Zoom, right?
Yeah, he can
Yeah.
log in Zoom and share the
Yeah,
slides.
yeah.
So then we can connect this.
This screen.
So we need.
We can directly show the Zoom screen here.
Yeah. So for that, oh yeah.
We don't need.
And then we need.
Yeah. Yeah, he can use it.
Zoom, how to internet?
Zoom.
Oh, I do come. Okay.
Yeah, do you sign off again? I did not see the Zoom. Yes, sir. Something.
Maybe you just type Zoom here. 831
Hmm?
831 7318 1873 73 73 last one is 831 7318 1873 no, not Jingsheng. Passcode is next. This is the password.
I can have it all.
Yeah, the passcode.
Do I have no password?
Yeah.
No
So
password.
here you type.
Just no. No password. No password. Yeah.
Next step.
If you click the link that I have sent to you directly,
Can you again check your email?
It's 17318 187. It's not asking passcode. Okay, let's just start.
No, there's no internet.
Um, connected. Now it's connected. Oh, internet.
Yeah, no internet.
You are on hotspot? Yeah.
Can you ask NQ past?
Let's
For that, we need to contact IT.
Oh,
okay, okay, now the first question. So mag capital M, capital S. M.
internet. Yeah, it's lost it. Thank you. Thank you. Thank you. Which one?
Maybe you have to. No, yes,
Oh.
okay, now.
Recording in progress.
Okay, share your screen. Share your screen. You can use this. No need for your video. No need for your mic. We use this mic. Share screen. Yeah, can we reduce your audio? Yes.
Which screen we have to?
Yeah, you have to share the screen. Okay. Done. No, no,
I mean, no, here we need to change. This, yeah.
Okay, let's get started. Good morning, everyone. So my name is Prem. I'm an associate professor here. On behalf of IEEE Magnetic Society and NTU Singapore, it's my pleasure to welcome you to this symposium. So this symposium has been happening for the past 12, 13 years. And I could see some of the participants who participated as students are now faculty members. So this is not the first time. We have also seen the same thing happening in the past. So without further ado, let's get started with this morning session. I'll pass the mic to the chair, Varun. Okay, Varun, to start the session. Yeah.
Yes, the laser is the laser.
No. From here. It's on my screen.
Hello, good morning, everyone. Welcome to this IEEE Magnetic Symposium. This session will start with the plenary talk given by Professor CHEN Jingsheng, and he is IEEE Distinguished Lecturer for this year. So this is our fortunate that he is here, and he will be talking on symmetry breaking by materials engineering for spin orbit torque technology. So let's welcome Professor CHEN Jingsheng.
Okay. Firstly, I would like to thank Prem to organize this meeting and they invite me to here to give this actually my next teaching lecture, this talk. Today, I would like to very happy to here to share with you about the symmetry breaking by materials engineering for spin orbit torque. So before starting my talk, I would like to give a brief introduction on the IEEE Magnetic Society, which is required by the this IEEE Magnetic Society distinguished lecture talk. In the first division of the Magnetic Society is to be the leading international professional organization for magnetism and for related professionals throughout the world. And actually, I think in the 2020. There are more than 3,000 regular and student members. And there are a lot of local, local chapter activities and lectures. I think this is one of the local, chapter activities. And the IEEE Magnetic Society has sponsored a lot of conference, which commonly we know the Intermag, 3M conference, KMRC. Another one, I think there is a very good. Summer school where this is free for graduate students. They will support your accommodation, flight, everything. Actually, this is very good for for graduate students. Due to the pandemic, in the last 2 years, this is canceled. I think next year will be Zoom. So and actually my next executive member, the registration discounts and the student travel support. And definitely, in one word, you are encouraged to join the IEEE Magnetic Society as a member or regular member or student member. That's done. For details, you can log in to this website. And here is my outline for today's talk. I would like to first give a brief introduction on spin up torque generation. Bark-like SOT generation in single ferromagnetic layers, and then we discuss some field-free switching or problematization by breaking mirror symmetry. Which here I show some examples. We use the field-free switching problematization by lower crystal symmetry and also by lower magnetic symmetry. So for people know we commonly switch the magnetization by using magnetic field, which is generated by passing the current through a coil. In the early of this century, that means after 2000, the people start using the electric field to switch magnetization due to the energy efficient by using the electric field, which because by using the electric field, there's no current, there's no dual heating. But when we do some symmetry analysis, we found out the electric field is actually parity odd and time reverse symmetry is even. Well, for the magnetization, the parity is even, but the time reversal symmetry is odd. So from here, we say the symmetry does not match. So therefore, it is impossible to purely use the electric field to switch the magnetization in 180 degrees. So definitely you can use the electric field to modify the magnetic anisotropy and the magnetization, and even you can change the magnetization z-axis, but less than the 90 degrees. And I think just recently, a few days ago, Avalanche and the UMC has announced the 16 gigabits per square inch STM RAM. So I think this is based on the spin transfer torque. You know, spin transfer torque actually is one electric current pass through a magnetization that we call the 50 layers will generate a spin current. This spin current will, when they pass through another ferromagnetic layers, will exert a field-like torque or non-damping torque, and then switch the magnetization. So here, the spin current and polarization, which is has a similar symmetry with the magnetization, which is parity even and temperature odd. As I mentioned, this this not only the Avalanche, which is based US-based companies, and UMC. Actually, the Samsung and the GlobalFoundries had commercialized this STM RAM in a 2 years ago, I think. Based on for Samsung, it's based on the 28 nanometer node EM RAM, and GlobalFoundries based on the 22 nanometer node. So from here we can say, okay, when electric current pass through this one ferromagnetic layers, suppose suppose there are some angles between the two ferromagnetic layers. The angle is theta. When the charge current pass through the first ferromagnetic layer, okay, they will generate electric current, which polarization is parallel to the magnetization of the first ferromagnetic layers. When they pass this, spin current pass through the ferromagnetic layers, they will exert a torque on the second ferromagnetic layers, and then switch the switch the magnetization of second ferromagnetic layers. But here we should note it's different from the linear momentum. Here, linear momentum change, but for the angular momentum change, only the amplitude has changed. Okay, well, so amplitude remain constant, only the direction is changed. So based on this, we have this dm square, amplitude of dm square dt equals 0. Based on this, we can say only the component perpendicular to the m of the electromagnetic moment can be transferred to the second ferromagnetic layers. That means the parallel component does not generate any torque on the second ferromagnetic layers. So in this case, when these two ferromagnetic layers are purely parallel or anti-parallel with each other, there's no any torque. Okay, from here we can see this STM RAM, there is certain disadvantage. Since if in order to get highest TMR ratio, we have to make sure that two ferromagnetic layers anti-parallel or parallel. So in this case, there's no any torque. So we cannot switch magnetization. But when we use a large rating current, the temperature will increase. We deviate the magnetization away from the parallel or anti-parallel directions. So you can use the current to induce magnetic switching. Another one, the reading path and the writing path share the same path. So therefore, the space layer, which normally magnetic oxide, will be deteriorates after many cycles. So therefore, the endurance become problems. So therefore, for the disadvantage of STM RAM, that is endurance problems. And another one is the speed, because we need to increase the temperature. Increase the temperature. So which takes some time. But recently, SOTM RAM. So from here, the reading path and writing path are separated. So therefore, there's no endurance issues, and also the spin current is generated from the heavy metals. So therefore, we can use in the parallel or anti-parallel configuration. So there's no, even though there's no temperature increase, we can still switch the magnetization. So in this case, the speed is not the issue. We can use the faster speed devices. But definitely there are some other issues for the SOT and RAM, large SOT efficiency. For small spin current is required. Us to searching for some suitable heavy metals. And also we need to break the symmetry for free switching. This spin Hall effect actually is due to the charge current pass through the heavy metals, they will generate a spin current. For example, here is along the vertical direction, the spin current, and the polarization in the y directions. So, and then this spin current, okay, with the polarization in the y direction, we exert torque on the ferromagnetic layers. The mechanism of the spin Hall effect, okay, there are two kind of mechanisms. One is the intrinsic scattering, okay, it's based on the Bilayer curvature, okay, which induce a monopole magnetic field, which induce the electrons with the spin up, spin down, separated in the transverse directions. Another one is the extrinsic effect. We call the sun-jump scattering and the circle scattering. This is when you doping some elements, impurities in the materials, definitely this will generate electric field gradient, and which will cause the spin-dependent scatterings. And in order to generate a net spin of torque, we need to break the inversion symmetry. For example, here, if there's with this ferromagnetic layers, okay, if the on top and bottom there are the same heavy metals, we suppose the interface are same. So therefore, you can see the torque exerted on the ferromagnetic will be cancel each others. So this with the inversion symmetry. But if we remove the top layers, okay, now the bilayer structures, or the top layer interface and bottom layer interface are different. This will induce some, this will cause the inversion asymmetry. So we can generate a net spin up torque on this ferromagnetic layers. But from here, we can say when the spin current injected into the ferromagnetic layers, they will generate, okay, there are some consequence. For example, spin accumulation, spin injection, and then spin transfer torque exerted on the ferromagnetic layers. So from here, we can say this efficiency in the bilayer structures will depend on the interface properties. For example, okay, the spin current transmission transparency is very important, which affect the SOT efficiency significantly, and also the spin scattering or spin relaxation at the interface will also affect the SOT efficiency. Another one is the current, due to the spin current spin polarization defacing in the ferromagnetic layers, this can be only used for the ultra-thin magnetic films. So in order for the high density, we know, okay, we have a thermal stability, factors which should be larger than 40 to 60, depending on the data, the time of data stored in the bit. For 10 years, we need to larger than the 60, which the thermal stability factor, which is equal to KUV divided by KBT, this V is a volume of, recording bits. That means from here, the ultra-thin film need a larger size of the bit. So it's not favored for the ultra high density. So from here, if we use this kind of bulk materials, there's no interface. We suppose one layer, atom layer of heavy metal atoms, one atom layer magnetic atoms. So therefore, alternatively, we're changing their composition along these directions. So therefore, we can also break the inversion symmetry. So therefore, there's a net on top on these materials. So this inversion symmetry induced by the composition gradient. So from here, we choose the L10 and planar thin films. In this case, this L10 and planar film have the special structures, which are atom layer, platinum atom layer, ions alternatively stuck along the Z directions. So we choose the gradient is 0.5% per nanometers, and the films still show very good propylene entropy. And we make the device. So from here, when we apply, definitely here we have still apply a longitudinal field in the current directions. When we apply the electric current, we can switch magnetization from the up to down, and the reverse the electric current we can from down to up. When we change the magnetic field directions, we can see the magnetization. The switching part has changed. This phenomenon is similar to the SOT in the bilayer structures. So therefore, we think this SOT, we call the bulk like SOT, is due to it's generated in these materials. And we still use the polar mock to visualizing the domain switching in these materials. From here, we can say when the current increase, okay, when the current increase, the domain is increased, the domain starts reverse, and with the current intensity increase, all the domain has been reversed. When we change the current directions, okay, the domains has reversed to another directions. So from here we can say, okay, in order to rule out the interface effect, we have done the thickness dependence here. We have done the thickness up to 60 nanometers. But for this kind of materials, we have to make sure the chemical order degree should be kept same. The chemical order is defined by how good is the atom layers aligned along the C directions. So from here we can say, okay, for the chemical order, for all the thickness is quite similar. So and also maintain very good propylene isotropy. From here we can say the effective field due to the SOT is increased with the thickness. So therefore we say this SOT is induced by the bulk. Okay, it's by the bulk, it's not from the interface. Actually, we have done how this SOT effect field relate to the composition gradient. From here we can say this increase with the composition gradient. And we have done another experiment that further confirm this SOT originated from the composition gradient. From here we can say we reverse the gradient. Okay, for example, the first one is the PT increase, okay, with along the Z direction. The second one is the PT, okay, decrease along the Z directions. But both show the permanent isotropy. But from here we can say the switching polarity has changed, has reversed. This further confirms this switching is due to the composition gradient. And then we discussed the field-free switching or perpendicular magnetization by breaking the mirror symmetry. We know in order for the practical application, we have to, using this field-free switching. And for the magnetization switching by SOT, we know that through the bilayer structures, there is an anti-damping torque and a field-like torque. Only the anti-damping torque will play the main roles to switching the magnetization. So here we will not discuss the field-like torque. For the anti-damping torque, there is an effective field along the current direction. So therefore, it will rotate this magnetization from the up to down, right? And so therefore, the up direction is not stable. And then when the magnetization is down, still the effective field rotate the magnetization to the up. So therefore, the down is also not stable. And then we can use our external magnetic field in the current directions. We just compensate this effective field. So therefore, in this case, the down is more stable than up. So therefore, by applying this current, we can say we can switch magnetization, deterministic switching magnetization from the up to down, right? Because down is more stable. So also we can do some symmetry analysis for the deterministic switching for perpendicular magnetization. We know there are two kind of polars, two kind of vectors. One is a polar vector, the other one is the axial vectors, also called pseudo vectors. When we apply the mirror symmetry, these two vectors show different behaviors. For first one, when the polar vector parallel to the mirror planes, their direction does remain unchanged. When the polar vector perpendicular mirror planes, will reverse their directions. And for the axial vectors, from here, opposite to the polar vectors. When this axial vector parallels the mirror plane, they will reverse their direction. Perpendicular mirror plane remain unchanged. So we can use this symmetry analysis to analyze the switching system. For example, in the left side, there is a electric current. There is a perpendicular magnetization. When you apply the mirror symmetry, you have the electric current does not change. Only the magnetization has reverse directions. So therefore, this indicates just when you apply this current, this direction of current, the polarization up and down is energetically equivalent. So therefore, you cannot use this electric current to switch to the magnetization. And when you apply a magnetic field, external magnetic field along the current directions, so when you apply the mirror symmetry, so therefore this magnetic field should reverse that direction. But since this applied, you cannot, it does not change direction. So therefore, we see this applied magnetic field has breaks the mirror symmetry. So therefore, the deterministic switching has can be induced. But definitely this external field is not practical for the real applications. So okay, so we need to find other methods. Actually, in the society has proposed a lot of methods. Okay, the first one, the anti-ferromagnetic materials coupled to the ferromagnetic materials, which generate a unidirectional anisotropy. This unidirectional anisotropy in the MH loop, they show exchange bias. This exchange bias actually is behavior like an external magnetic field. Okay, so therefore break the mirror symmetry. So based on this method, we can switch the magnetization, okay, deterministically. And also use the wedge structures. This, when you apply the mirror symmetry, this, geometry should be changed, but they cannot change, right? So they break the mirror symmetry. So this also demonstrated can cause a deterministic switching of the perpendicular magnetization. Another one, or by using the macro fabrication method, you change the z-axis, or you tilt the magnetization directions, and or you use the control the z-axis by the deposition or string. Okay, actually in my group we have done this. I use the string and the deposition process to control the tilt the z-axis away from the perpendicular magnetization to one direction. So this method also can cause the deterministic switching of perpendicular magnetization. And the other one, okay, just put the third layer, this soft magnetic materials, okay, along one direction. So this behave like an external magnetic field, breaks the inversion symmetry. So this also can cause okay, deterministic switching. But here from here we can say, or we control the extra axial vectors. But also we can use a polar vector to break the mirror symmetry. For example, now the polar vector must parallel, perpendicular to the mirror plane. So this also has been demonstrated. When you apply an electric field perpendicular mirror symmetry, we can cause a field-free switching. And but all this by control the polar vector or axial vectors. Now we using some local symmetry crystal to break the mirror symmetry and induce the field-free switching. Actually, this firstly proposed by the Professor Ruff group in the Cornell University, but they use the tungsten ditelluride materials. These materials no mirror symmetry in the AC plane, but there's the mirror plane in the BC planes. So he demonstrated by using the SUT FMR. When the current is perpendicular to mirror planes, there is a auto plane spin on top. This auto plane spin on top can switch in principle can switch the perpendicular magnetization. And when the current parallel to the mirror planes, there's no auto plane torque, can be generated. So, but they only demonstrate, this auto plane torque exists, but they does not demonstrate, the switching, the field-free switching on the magnetization. In my group, we have also do this. We use a strong ruthenium oxide, as a ferromagnetic materials. From here, we can see they show perfect permanent anisotropy. And they use the exploited as a foliated tungsten ditelluride as a on top of this strong ruthenium oxide. And we use the polarized element to define the A-axis and B-axis. And then we make the device. Actually, we have demonstrated when the current perpendicular mirror plane, will cause the zero field switching and the free field switching. And the current parallel to mirror planes, there's no field free switching. And furthermore, we demonstrate another low symmetry materials, this cobalt PT and the copper PT, which is iron 1 structures. This structure had a one atom layer, copper or cobalt, one atom layer PT along the 1,1 directions. Actually this is a bond group is a R3 by M, but at the interface, if we make the double layers, the interface is symmetry reduced to the 3M1. So definitely it's a threefold symmetry. Definitely we have a three high symmetry axis. The three high symmetry axis means that parallel. This direction parallel to the mirror planes. There are low symmetry axis refer to the direction perpendicular to the mirror planes. So and then we make the materials sputtering. From here we can see we can get good L11 copper PT. So base is characterized by the 1,1 superlattice peak and also the TM structures. So very good perpendicular anisotropy, and the in plane is isotropic. So from here and then we make the device along different directions. Here the 1 - 1 0 direction refer to the low symmetry directions. Based on this, we have demonstrate when the current along the low symmetry axis, that means 0 direction, 0 degree, you can observe the field free switching. And in the high symmetry axis, no field free switching. And in another low symmetry axis, they reverse that directions. Reverse the switching priority. In one word, we can say, in summary, we can say this switching follow the threefold symmetry. Definitely, we can also evaluate the auto plane torque and auto plane effective fields, which is also follow the threefold symmetries. Switching and auto plane effective field also follow the threefold symmetry, which is same as this crystal structures. So therefore, we have done some analysis based on symmetry, by collaboration by the Orlin Manchun, and we based on the Kubo linear response series. The torque is linearly proportional to the electric field. And then when we apply this symmetry to this this torque, we can get one damping-like torque and one extra torques. Normally, for the common materials, only one torque, damping-like torque. And the field-like torque is 0 order linear symmetry, linear response coefficient. But for the 3M torque, we can from here we can see if the perfect in the z directions, my, mx is 0, so the 3M torque becomes 0. So actually we understand this scenario. The damping-like torque we will switch magnetic along the y directions, and then the 3M torque start to work. So based on this, we have a substitute. This phi m equal to the phi plus 90 degree because the magnetization is always 90 degree different from the electric field. So from here we can get this torque is a threefold symmetry. And also we have done some macrospin simulation which consists in our experimental results. And since this intrinsic property, low symmetry, right? It's intrinsic property, so it has very good endurance. For example, the AFM, FM bilayer structures, right? Due to the the temperature increase will cause the aging effect, right? The rearrangement of the antiferromagnetic materials. So therefore, after 12 switching loops, the switching priority has deteriorates significantly. But for us, we have demonstrated about 2,000 switching loops. We take 1 month because 2 man-pound for each loop. And also have demonstrated the only up and down, up to the 5 times to the 10 to the power 5. But this, yes, the device is broken, but the broken is not device broken, it's the electrode. Electrode is broken because of large contact resistance. And now we use the composition gradient and the threefold symmetry. We have a design another materials, FCC cobalt PT, which is the permanent anisotropy, right? But close to the interface, they form the layer structures. The cluster is the layer structures. So based on this, we have deposits FCC cobalt PT materials. From here, we can say, okay, threefold symmetry, and also with increased thickness, the magnetic structure will decrease because the layered platelet, okay, structures is close to the interface. So from here we can see also some gradient, composite gradient, and then we use the results to evaluate the anisotropy of the cobalt platelets, because when the bonding in the lateral direction is larger than the vertical direction, right? That means they form the cobalt platelet. We have demonstrated by using the examples, and definitely, the single ferromagnetic layers. Okay, we can switch it. We call it self-switching. We did not apply any field, just use electric current. We can self-switching these magnetic materials. From here, it's a threefold symmetry. This 5 minutes. 15 minutes. Okay. So okay, now we just give a very brief introduction on the magnetic asymmetry. Just actually for the L10 using manganese, L12 using manganese 3, and gamma using manganese, right? Their spin texture are different. For in the bulk materials, it's a collinear structure for L10 phase. L12 is a non-collinear, and gamma using manganese is quite randomly orientated. When we deposit the films on the synchronous substrate due to the string effect, the spin has been taken away from the perpendicular direction to the 1-1 directions. So the near vector along the 1-1 directions. But for the L12 and the gamma phase does not change. And but when we do we introduce the magnetic mirror symmetry. The magnetic mirror symmetry just the crystal mirror symmetry times the time reversal symmetry. So from here we can say the polar vector, since it's even in the time reversal symmetry, when we for the magnetic mirror symmetry they remain unchanged. But for the X vectors, because it's odd in the time reversal symmetry, so if for the magnetic mirror symmetry they have a change compared to the crystal symmetry, mirror symmetry. For example, this is when they perpendicular to the magnetic mirror symmetry, that direction is reversed. When the parallel to the mirror symmetry remain unchanged. So actually, when we do some detailed analysis for this L12 and the L10 phase, using manganese, we find out there exists a mirror plane, which is a 110 plane. So from here, in the magnetic symmetry is lower than the crystal symmetries. High crystal symmetry has a 4-fold. Okay, but here, for the magnetic symmetry, there is a mirror plane on the 110. So actually, we use the angular dependent STFMR, to demonstrate, exist the outer plane spin polarization. The STFMR here, the technology, I will not go to details. I think, we just give a brief discussion here. When your AC current, pass through these bilayer structures, since there is a torque generated from the ether magnets, this torque will generate, will cause the magnetic layers precession. Oscillation along the, since the AC current, right? Due to AMR effect, the resistance is also changed with the current directions. So therefore, they will induce a DC voltage. We use the DC voltage to calculate the damping like torque and the field like torque. So from here, we can say this spectrum will decompose into a symmetry part and the asymmetry part. The symmetry part corresponding to the field like torque, damping like torque. The asymmetry part corresponds to the field like torque. So therefore, based on this, you can calculate the SUT efficiency. And here, in order to get a large signal, we use the apply magnetic field along the 45 degree, which is the highest AMR effect. And but this angular, we change for angular dependent, we change the magnetization. Change the magnetic field along the in-plane directions. So definitely we need to derive the how the voltage change with the field directions. So definitely based on the Lipschitz Gilbert density equations. But from here we can see definitely SOT must one of the two types, right? Damping like torque, anti-damping like torque. But here is difference here. The coordinates are different. For this Landau-Lipschitz, okay, Gilbert, RRG, and the Swansky equation, right? The coordinates refer to the magnetization. The magnetization refer to the magnetic field direction, the AC magnetic field directions. So now when we change the lab, right? In the lab coordinates, we need to do some coordination conversion. So based on this, we have derived this VS and the VA. This VS is the symmetry components. VA is the asymmetry components. So therefore, the first set refers to AMR effect. The rest, for different components, we have different origins. Here we summarize here. Okay, now we only consider about the fifth. It's due to outer plane spin polarization. That means as long as there is some SC and AC exists, the constant, right? We see there is an outer plane spin polarization. So therefore, we use this method. We really has demonstrated there is a AC components which correspond to the outer plane spin polarization. And definitely you can do some analysis based on the symmetry. You can derive this is there's really due to the magnetic asymmetry. Definitely we have done the first principle calculation here. When the near vector is along the c-axis along the a-axis, there's no this component perpendicular outer plane spin polarization. But when we pivot the spin polarization, we show some outer plane spin polarization spin Hall conductivities. But for the L12 under both cases, they exist. Outer plane spin polarization. Well, for the random lines, for the gamma magnets, we did not see this outer plane spin polarization because there's no magnetic asymmetry. So this is a summary. Thanks my two PhD students and two postdoc and 4 PhD students and some collaborators. Thanks for your attention. Yeah.
Open for questions, discussion. We have enough time.
Go to slide 16. Slide 16.
16.
16. One.
Oh. Right. Oh, this is quite high. Yeah, quite high. And sulfate is still 20 to 30. I think 30 kilos there.
So still 1,000 posted of in plane field.
Yeah. But this I think this we mentioned this partial switch actually. Partial switch. Only maybe 30%, 40% switch because it's when you have a large current, right, the temperature increased.
So you said for STT and RAM, we need to wait for the temperature to rise. But at room temperature, there's some thermal fluctuation, right?
Yes.
Isn't it enough, or we need more temperature?
Because when as long as you have some current, there's some Joule heating, except that the time very short. Right. So therefore, normally in our experiment, our lab is measurements. Definitely we involve thermal assistant switching because our switching time is in the microsecond or millisecond, right? This this is Joule heating is quite large. If you go to a nanosecond, then maybe the switching mechanism also will be different. Normally we currently is a thermal assistant switching. It's not based on the domain word, nucleation and the propagation method. Actually, we have demonstrated, when you apply the magnetic field, they will show the domain word as, downward. From here, you can see, right? When you apply the in-plane magnetic field, they show the downward expurgation, downward nucleation and expansion. But if you only use the, outer planes polarization, right? Faster, okay, you can say is only nucleation. It's not a downward expansion. Because when you apply the in-plane magnetic field, it cause some okay, what I say, this downward spin texture has changed, right? Okay, to the clarity effect.
Okay, let me ask you. I have a question. How you control the gradient in G direction?
That's definitely you can use a sputter, right?
But in sputtering, usually it's in plane, but you saw it's in perpendicular.
Yeah, perpendicular. When you deposit, you just keep changing. You keep changing one power.
Okay. Okay.
It just fix for the unplanned. Okay, you fix one, and you decrease or increase another. This can be program controlled.
Another question I have, you use this ferromagnetic material, FM1, FM2. So is there any specific property like, let's say, permalloy? Once we are using permalloy, which is very soft and then very low anisotropy. The other is iron cobalt. So how do you choose that ferromagnetic material for such devices?
Which permalloy? Which device? In the 3-layer?
In any device for this, is there any?
Okay, because for the STFM, we choose a permalloy because permalloy has a large AMR effect. AMR, lot of AMR effect. That means the one it measures the STMR signal is larger because that's when the sign value depend on the AMR effect. That's why we choose a larger AMR effect materials. We choose permalloy. But the switching we use the second harmonic measurement. Okay, does not depend on the AMR effect. So therefore, you can use a second harmonic to measure. This is depend on the method test. Okay.
And this ordering, how the ordering is controlled with the symmetry within that material.
Which materials?
Symmetry is saying that the symmetry is very important factor here.
Yeah.
But sometimes when we increase the thickness, the symmetry go away. It can be a disordered material. So,
but definitely that's okay. Really depend on the
my question may not be very.
Yeah, it's not. I agree. This one may not be really practical. Okay, you need a single crystal.
Yeah, that's right.
Yeah, this may not be okay. For the practical application, may not be good. But we still find some extra talks, right? Some physics, we can find some. Okay, not only in the past, for the PT, for tantalum, even the amorphous, they can still generate the torque. But here, only the crystal symmetry, okay, can generate torque. It all depend on the crystals. That's definitely depend on the Bloch wave, electron wave, okay, Bloch wave, propagation, right? And this one, allow me, to associate this kind of torque maybe related to the orbital Hall effect, because orbital Hall will affected by the orbital hybridization, which definitely depend on the crystal symmetry. Okay, so the origin is different. In the past we say the spin orbital coupling is from the atomic nuclear, right? But the cobalt is a good permanent anisotropy, right? It's light materials. But where the large permanent anisotropy come from is still come from the spin orbital coupling. But that spin orbital coupling is due to the spin come to the lattice. So the lattice itself is also the spin orbital coupling. We maybe also generate some new torque.
Any questions? Other question? Okay, let's thank the speaker again. some time. Yeah, oh, there's one online question. So I
Hi, yeah, thank you for a wonderful talk, Professor. Am I audible? Yeah, so I wanted to ask, as you mentioned, that the SOT is mainly observed from the bulk, and as in the slide, it was the maximum thickness was 20 nanometer. If we increase the thickness, will the SOT be observed from the bulk, and what's the maximum thickness we can go for building the material so that the SOT will be observed?
Sorry, I cannot, okay, get your point. I just, okay, can you repeat your question again? Sorry.
Yeah, sure. So, as I mentioned in the slide, you said that the SOT was mainly because of the bulk after performing experiments by increasing the thickness of the material to maximum of 20 nanometers. So my question was, what is the maximum thickness we can go so that we can observe the SOT?
Maximum
Maximum thickness of the material, yeah.
Oh, but here we demonstrate the 60 nanometer, right?
60? Sorry.
We have demonstrated 60 nanometer.
Oh, okay, 60 nanometer. Okay. Yeah.
Okay.
Thank you, Prof.
It's in your
Recording in progress.
Yes, so our next talk is a keynote talk given by Professor Avsar from NUS. So he'll be talking on black phosphorus spintronics. Let's welcome the speaker.
Thank you very much. Good morning, everyone. I'm Ahmet Avsar. I just recently joined the National University of Singapore to the Material Science and Engineering Department. So I'm an NRF fellow. And today I will be talking about the black phosphorus spintronics. And before starting my talk, I would like to also thank for the invitation. Once I got the email from Odo, I was excited because I think it was 10, 11 years ago while I was first year PhD, I joined one of these symposium, and I'm glad to see that it's still running, and hopefully I will be able to contribute. Okay, so I will not go into detail much, but so you are already quite familiar. This heating problem with the current devices, with the Cmos, that the heat flux has been increasing as we are improving our devices. And for example, here you can already see image from a mobile phone processor claiming that the processors are like melting the butter much less compared to the competitors. But we have a big problem. And we had a similar problem in the past, indeed with the bipolar technologies, and it was just also increasing quite dramatically. And then by changing the technology from bipolar to the CMOS, we have already earned like 10 years. And the question is, what will be the new technology for beyond CMOS? So here I put a little about my general research focus. So I am quite closely working on the exotonic transistors by creating some interlayer exotones and diffusing and manipulating them. And the second research direction I have is spin transport, but here we are using the pure spin current to propagate the information, and hopefully we will be also manipulating some. And we are also doing quite a lot with the novel charge transport, like such as defect-induced magnetism, etc. So these are all relevant to this beyond CMOS that I have been describing, but today I will be mostly talking about the spin transport, and as a material system, I will be talking about the black phosphorus. So I will give a very general brief introduction to the spin transport, the current status, and then I will be introducing you the black phosphorus, and I will give some of its key spintronics properties. And then later on, I will be also discussing that this material is highly anisotropic. It has a puckered crystal structure, and I will be showing you that the spin propagation along the different direction of this material is different. So it can also give us some opportunities to create devices which are based on the directional control of spin transport. Then I will give a summary. Okay, so of course, before these 2D materials like graphene or black phosphorus, spin transport has been already, it was already demonstrated in bulk materials. For example, with the metals, it was shown that in aluminum, copper, or silver, the spin transport works quite nicely. It was even working at room temperature. So here I already listed some of the advantages and disadvantages of the spin transport with conventional metals. So the advantage, the main advantage for the metals is it works at room temperature, but the issue is the relaxation lengths, meaning like how long you can propagate this spin current is quite limited in the metals, and the signals are also extremely small. So if you want to do like spin transfer torque studies, etc., with the pure spin current, you will need much more spin accumulation in your channel. So they might not be the best material choice. And of course, over the years, it has been also quite improvement in the metal spintronics. For example, by improving the contact interfaces by a group in Japan, they managed to increase the spin relaxation lengths up to 6 microns, so which was quite good in terms of the spin transport materials. And with the spin transport in semiconductors, there have been also quite nice materials like gallium arsenide, silicon, and germanium, ultra thin films like 100 nanometer, and they have demonstrated spin transport up to room temperature, no, at the beginning around up to 80 Kelvin. And they have also, again, some advantages and disadvantages. So, for example, the advantages, the spin lifetimes are extremely long in this semiconducting materials, especially at low temperature. But whenever you are increasing your temperature around 100 Kelvin, almost all the materials are collapsing. So there was also a breakthrough. So by again improving the interfaces for the better spin injection efficiencies, it was demonstrated that spin transport can exist in silicon up to room temperature. But as you can see, again, the spin signals that you create in your non-magnetic channel material is quite low. So here I listed the advantages of and disadvantages of the metals and the semiconductors. And so the hype with the graphene was, it was believed that it will inherit the advantages of the both metals and semiconductors, meaning that since this material has extremely high mobilities, and since it's just like carbon 12, no spin orbit coupling strength is extremely small, and there is no hyperfine interaction. So all the expectation was this should translate into very long spin relaxation lengths in room temperature. So this was the first experimental results, and the results were both quite positive and also a bit negative, because the good thing was it was working at room temperature, but the bad news was spin relaxation lengths were also not that long. And of course, since then, there have been lots of breakthroughs in the field. So, for example, it was shown that in like 5-6 years ago that you can improve the spin transport properties of these materials up to 10 nanoseconds, or you can transmit the spin information of over 30 micron, which is the highest ever measured in any material system. So graphene still works, but still like orders of magnitude smaller than what the theory is expecting. So it was shown that you can also obtain such long spin relaxation lengths or spin communication in large scale CVD graphene. And also you can do some, you can build some simple spin circuits based on already with this large scale graphene. But for me, like one of the most important or most exciting part of the 2D materials is like the gate tunability. So these are extremely thin materials, and if you can apply electric field, you can change something. But unfortunately, you cannot change much with the graphene because it's a semi-metal. And as you can see here, the residual graphene just changes like a few times with the gate voltage. And indeed, the spin current is also almost showing no change with the application of the gate voltage. So if you think about this beyond Cmos era, so you need also the gate tunability so that you have an extra knob. So this is something that we tried with the bilayer graphene. So bilayer graphene is a bit different. So it's not like a semi-metal like monolayer graphene. So if you apply a perpendicular electric field, you can induce some band gap in this material. And what we were doing is like we were measuring the spin transport as we were opening the band gap. And so as you open the gap, and then you could see that you can also control the spin current like a propagation in this material. But the issue is like it only works at extremely low temperatures. So it's not very practical. So that's why we got interested into the black phosphorus, which is like a natural semiconductor. And it has also quite a lot of interesting properties, which makes it quite appealing for spin transport studies as well. So that's what I will be discussing now. But before starting showing any results, so let me just remind you with the measurement geometries and how we are measuring so that it will be more apparent for you later on. So this is something we call non-local spin wall geometry. Here, what you do is you are sending the charge current here. So the charge current is only propagating in this area, but you are creating already a spin imbalance here. So these are ferromagnetic contacts. So whenever you inject the charge current, it also becomes spin polarized, right? And the spins are not only diffusing here, they are also diffusing here. And in this area, you don't have any net charge current propagation. So therefore, all you will be measuring at the other side of the device is basically any signal coming from the pure spin current rather than any charge contribution. And what we do is like we are applying a magnetic field in plane along the easy axis of the ferromagnet. And so that these injector and detector electrodes, they are parallel or anti-parallel to each other. And if they are parallel, you have a different resistance state. And if they are anti-parallel, so the resistance is changing, then it's switching. So you have this rectangular shape device, and which would be kind of proof that you have pure spin current propagation in this material. So you can get this delta R, and you know the L, and basically, here I have added here. By varying this delta R as a function of L, you can get the information about the spin relaxation length in this material. So this is one way. The second way is you have again the same geometry, non-local geometry, but this time you're applying out of plane magnetic field. And what happens is the spins which are already in your channel material, they start to process along this magnetic field, and you get this kind of this oscillating type signal, which we call it Hanle spin precession curve. And from here, by doing the fitting, you can directly get information about the spin relaxation time and the spin diffusion constant. And from there, you can get again information about spin relaxation length. And the third measurement that I will be showing you today is what happens. You apply again the out of plane magnetic field, but this time you apply a very strong field. And in this time, because in the previous case here, we were applying quite small field, and the magnetization direction of the ferromagnets were still in plane. But if you would push a bit more, apply much more higher fields, then the spins will be, these ferromagnets will have out of plane polarization. So therefore, whenever you have the spin current propagation here, the spins are pointing in out of plane. So this is different than the previous measurement, because in the previous measurement, the spins were precessing in plane. So basically, by doing this experiment, you can get an information, what are the spin properties once spins are aligning out of plane versus in plane, right? So basically, this is what I am saying. This is the Hanle curve that I showed in the previous slide, and the spins were just pointing in plane. And here at high field, we start to force the polarization direction of the injector and detector to be out of field, so that the spins this time propagating in the channels, they are out of plane. So you have this. So the question is like, by comparing the spin amplitude, the spin signal here and here, you will be able to get some information about something called spin anisotropy, like how is the spin lifetimes along the in plane versus out of plane direction. So I will be showing you how we are using this to determine the spin anisotropy in black ball source later on. Okay, so before showing you anything with the black phosphorus, let me show you the typical measurement we did with the graphene. So this is like a graphene encapsulated with the boron nitride crystal. So I will not go into detail, but the top HPN is serving as a tunnel barrier for efficient spin injection into the material, and the bottom HPN is working as a high quality substrate to increase the mobility of the devices. So these are the main measurements we have. So you see spin switch, Hanle, everything looks good, and this anisotropy that I was just introducing you here, the ratio of this signal to this signal, for pristine graphene we get exactly 1. Okay, so this material is isotropic. There is no difference if the spins are propagating in plane or out of plane. The spin transport properties are identical. So I will show you that this is completely different for black phosphorus. So let me briefly say why black phosphorus. So this is a semiconducting material, and you can thin it down to again a monolayer. And the material has very strongly thickness dependent band gap. So for example, the bulk of black phosphorus has a band gap of 0.3 eV. In monolayer it's like 2.1 eV. So basically with that you can control many charge properties and on-off ratios of the transistors, etc. And the second thing, I think this is one of the most important reason why we choose to work with black phosphorus is it has extremely high mobilities. So the mobilities in black phosphorus, it's approaching to 50,000 at low temperature, and at room temperature it's like 5,000. These are very comparable mobility values that we are using in graphene spin walls. And the last one is why it's interesting is the anisotropic. So the material is highly anisotropic. It was shown for the charge transport, thermal transport. The material is already anisotropic, and in plane along the armchair direction. Here is the armchair direction, and if for example, charges are diffusing towards here compared to here, so their mobilities are different. So that's also another thing which makes this material quite different compared to the other usual material. But what about for spin tonics? Why spin transport? Why black phosphorus is interesting is because you can see already this cropped periodic table is very close to the silicon, which is kind of the star of the material of the spin transport. And it's also phosphorus is also a light atom, so hopefully it means that it should have like small spin orbit coupling strength, which would transfer into long spinor acceleration lengths. And with this material now we have the opportunities of trying anisotropic spin transport because of its crystal structure, which was not possible with any other materials in the literature. And the material it has a centrosymmetric structure, meaning that the Elliott-Yaffe type spin scattering mechanism should be dominant. So what it says is like if your electronic mobilities are high, so your spin transport properties will be also high. So considering how long we have mobility, so the spin properties should be also quite interesting. And the last one that I'm not going to discuss today, but it has also 1/2 nuclear spin, which would also introduce more rich spin physics compared to the other materials like graphene, etc. Okay, so this is the device structure that we did here. We have again the black phosphorus, and the black phosphorus has some disadvantages as well that I didn't say. So it's degrading very fast. So you need to make all the devices in the glove box environment. And here we are using a very thin layer of HPN, like 3 layers of HPN for encapsulation layer and also for better spin injection efficiencies. And we just form the regular cobalt electrodes on top. And these are some example device pictures before and after the metallization process. So we do all these properties inside the glove box environment. So the surface of the phosphorine, black phosphorus, has never get exposed to any air or anything else. So we started with the very quick charge transport characterization. So we also saw some interesting physics here. So you can already see here some part of the devices like encapsulated with HPN, some part didn't. So they are directly contacted with the direct contact to the cobalt. So this is the area where there is no HPN encapsulation. How the charge transport looks like is a regular p-type transistor. And whenever you put a thin layer of HPN, your materials become, device becomes from p-type to the n-type transistor behavior by just inserting a very thin layer of HPN. So we were curious why this is happening. And so basically the work function is modified with the injection of the a thin layer of HPN. because of some charge transfer process that I will not go to detail. So basically, by just putting a thin layer of HBM between cobalt and black phosphorus, you can reduce the work function of this cobalt. Based on our calculation, it was around 1.3 eV. That's why you can go from P-type to N-type behavior. And similar results were also shown by Jingsheng group at Columbia. And we start to measure the spin transport in this material. So we were not extremely hopeful. So indeed, we start measuring immediately at low temperatures, and we could see like a clear spin transport signal. And then we also saw quite nice spin Hanle measurements in this black phosphorus channel material, and spin relaxation times that we extracted were around 3.2 nanosecond, which was it was much better than any graphene-based device that we have measured. So the spin transfer properties of this material was quite nice. And another thing that we could do was determine the spin relaxation mechanism. So the question is like how the spins are relaxing in this material. And to be able to understand that, one thing you can do is study both spin transport properties and also the charge transport properties as a function of temperature, and see if there is any correlation between the charge and momentum. And we did by doing the temperature dependent studies, and we could see that basically the ratio remains the constant. So basically, whenever momentum is being scattered, the spin also seems to be scattering. So that's also a good signature of Elliott-Jaffe type spin scattering mechanism, which you would anyway expect from this material system. And our collaborators did some calculations for us. So this is called spin mixing probability. So the one that they found theoretically is almost identical to what we measure in experimentally. So this might be trivial to you, but for the case of the graphene, these experimental theoretical values are differing from each other almost 1,000 times. So it was quite good that by doing the right fabrication in the glove box environment, and we managed to almost reach the intrinsic spin transport properties of this material. Okay, so now I will be also talking briefly about our work on anisotropy. So as I mentioned you that this material has a pucker structure. So it has some edges along the armchair and also zigzag edges. So I have listed like just the keywords here. So along the armchair direction, if your spins are propagating, so they have like higher electronic mobilities, and effective masses are also smaller. So small effective mass means also small effective spin-orbit coupling strength, right? And along the zigzag direction, the mobilities are lower, and also effective masses is also higher. So then the spin-orbit coupling would be different. So as a result, you would be expecting some direction-dependent spin transport in this material. And here we choose some black phosphorus samples, and we did quite a detailed Raman and to understand the crystal direction, so that we know which direction has the armchair and which one is along the zigzag direction. So I will not go detailed, but basically around the 50 degree was the one which we start to hit to the armchair direction. And we prepare the contacts accordingly. And this is just the basic charge transport characterization of this device. So we were seeing mobilities around 4,000 at low temperature, which was quite good samples to start with. So basically, we did some spin transport measurements with this sample. So as a function gate voltage. So here you can see that there is no spin transport until this gate voltage range, which can be kind of understood that the material was within the band gap. So your Fermi level was within the band gap. So there is nothing to carry. So it's okay. And then we were seeing a nice spin transport again, and then later on again, the spin transport disappears. So this part is quite strange because especially once your device is conducting even better, but you don't see any spin transport. So you have like this off, on, and off structure as a function of gate voltage. So I don't have time to go detail, but we did some basic simulations, and it looks like it's all about the computation between the spin conducting channel materials conductivity versus the injector electrodes conductivity. And so it's something called conductive mismatch problem. So whenever your contact resistance reduces considerably here, even though your device is conducting very well, you cannot effectively inject any spin current. So therefore, you cannot measure any spin transport. And we started to do also some out-of-plane spin anisotropy measurements. So these are the typical Hanle measurements that I show. So if you would measure this sample with the graphene, this high field range that you will see would be having the same amplitude. But in the case of the black phosphorus, what we see is the signal is almost like 5 times more than what you would get with the in-plane spin current, which is already indicating a very strong spin anisotropy in this material. And we did some simple approximations. And here, these are the values that we are extracting. So, for example, it depends slightly on the gate voltage that you apply, but we have a spin anisotropy around 5 to 6 in this material, meaning that the spins pointing out of plane, they have much longer lifetimes compared to the, as you can see here, in-plane ones. So the low temp, like in-plane spins have around 1 nanosecond for this sample. For other planes, it's around 7 nanoseconds. And here we did the negative field, but if you do also the positive field, basically they go to the same value. It's just because either all of them are fully out of plane or in plane. So they are parallel in both cases. So it doesn't make any difference. Okay, so yeah, the question is why the spin lifetime in out of plane direction is very strong, right? So it looks like there's an internal, like a magnetic field, which is forcing spins to be stabilized along the outer plane. So to be able to really get more information about that, we also did this spin wall measurements. So you remember, I was showing you these spin wall measurements in the one of the few slides earlier, where you would get this rectangular type spin switching effect. But in the case of the black phosphorus, we do see like a very strong spin dephasing effect, and which is most likely because of the something called G factor anisotropy in this material. And this was also measured in germanium in the past, and it's just about the crystal structure, and we are still investigating this effect. And the last question is, okay, we have a strong spin anisotropy in out of plane and in plane, but I also mentioned that this black phosphorus, it has the pocket structure within plane, so they have armchair and zigzag direction. So does it matter if the spins are pointing in armchair or zigzag direction? So is there also any anisotropy within the plane? So for that one, you can just compare the spin signals generated in the spin valve and the spin Hanle precession, because in the spin valve, you're injecting spins and they're just moving without any rotation. So they are just being exposed to the one single armchair direction. But in the case of the Hanle, you're applying the field and then spins are propagating, like rotating within the plane. So they are being exposed to all the directions. So by doing some simple simulations, you can extract the spin anisotropy within the plane. So that's what we got. So the spin anisotropy within plane, it's also depending on the gate voltage, but the highest value is around 1.8. And so this is also agreeing perfectly with the theoretical predictions done for this material. Okay, so in summary, black phosphorus is a new material with very nice spin transport properties. It shows much better spin performance compared to graphene, at least to my experience. And now we have also these direction control possibilities by controlling the spin lifetimes along some preferred direction. So here I just put some more. These are all published work. So these are the different materials which shows excellent spin transport properties. So these are published work compared to the other materials. And we have also some unpublished works which shows that the spin lifetimes in black phosphorus can be up to 15 nanoseconds, which is better than even the silicon. Okay, and we also see lots of good spin signal. Okay, so this is my acknowledgement slide. So my student at my former university and my collaborators at the US giving access for some measurements and crystals from the NIMS group, and the theory was done with the Regensburg. And I know I don't have time, but I need really students and postdocs. So if you know anyone around interested in the spintronics with 2D materials, especially within the regime of with the magnetic insulators and also some superconductors, very unconventional spin transport, I will be glad to work with them. So this is something that I'm now forming my group here, so I will need lots of manpower. So if you know, especially anyone, I would be glad to discuss with them. So thank you very much.
We have time for one or two questions.
So like in one of your slides, like you showed that the spin injector in the for the case of the spin wall measurements, there was a spin injection and the spin detection. What's the maximum length that you have set?
The maximum length for black phosphorus is around 6 micron. For graphene, in the state-of-art device, one group published it from Germany, they could see up to 30 micron. But their devices were also like 4 or 5 micron of the separation, but they did calculation that it should last up to 30 micron.
My point is like till what the maximum length till which like the signal can be captured.
Yeah, so the devices we are doing on the exfoliated samples, so that's why we don't make the devices too long. So typically we make it like 2-3 micron separation. But from the measurements, you can get information how long maximum you could be putting, right? So with the black phosphorus, I think we can put easily to 6-7 micron. For graphene, typically it's also around 4 or 5 micron, but there are some state-of-art devices, as I mentioned, which bring it up to 30 micron.
No, because I fabricated the graphene in one device. It's a 36 micron. I mean the one that you showed me.
Yeah, so if you didn't see the signal, it's most likely because of the spin injection efficiency rather than the spin propagation. The issue is like, can you put the spins into the graphene? If you can, most likely they will transfer over the such distance. The main issue is to inject the spin because you have conductive mismatch problem with graphene. Sorry, so I couldn't get the last part. So in the measurements we get some noise, but the noise are less than 1% generally. So for the contacts we are using e-beam evaporator method. So thermal doesn't work for the magnetic materials very well. We also use MBE, but MBE is very slow and it doesn't give like a much better result. So we are just using the typical e-beam evaporator. Sorry? Yeah, so in the yeah, right now I'm very interested in the magnons, magnon currents, etc. But the devices that we have been studying, there is no magnon, right? Yeah, so but me myself is very interested right now working with the layered materials, magnetic insulators, and study the magnon propagation in these materials. Cobalt is the easiest one. So we had lots of experience with the cobalt, that's why. But right now we are also trying these 2D magnets as an injector. So many groups are also using the permalloy, so nickel. So depending on.
Would this obviously be very sensitive to adjacent layer, such that if you have a very strong SOC adjacent layer, will it destroy the entropy of the process?
So based on the charge measurements, it seems that it's not having any impact. So people did this charge transport characterization of the anisotropy as a function of thickness. It has some slight dependency on the thickness, but even in the thicker crystals, they still see a very nice anisotropy along arm chain. So most likely it should be also, right? Because if you have the charge diffusion, which you get from the mobility, you should also have the spin diffusion because it's having Elliott-Yaphet mechanism. So most likely it should persist. But I think it's a very good question. Thank you. Thank you very much.
Your measurement is measure the spin transport. So I saw you have the non-local measurement. So
Yeah.
this method can make the spin accumulation.
Yeah. So
it's the same.
yeah, it's the same thing. So you are just measuring how much voltage you have. It's the spin accumulation
What's
that
the
you need.
difference between the spin accumulation and the spin transport?
It's the same. So spin accumulation means that how much polarized spins you are inducing, right?
Yeah.
And then, but once you induce this, they start to diffuse.
Oh, you mean the spin still can diffuse
Yeah,
on the
yeah.
non-local measurement?
Yeah. So that's why you can get the information about the spin accumulation.
Oh, yeah.
So you accumulate them, so you induce them, and then later on they diffuse, and then if you can put a contact close enough before spins die, then you measure.
Okay.
But if you know this distance
This distance, yeah.
and you measure the voltage, you can already calculate this amount of spin accumulation in your channel.
Oh, yeah, based on the spin, the distance and the spin
Yes.
accumulation.
Yes.
Oh.